Doing in the last couple days, but I'm losing my voice a little bit. I didn't realize it until I just started to talk loud, and I'm struggling to do it a little bit. So bear with me, and don't make me talk over top of you. Like, this is as loud as it gets, and I want to be heard. It's a professor thing. We just like to talk and be heard. That's why we do what we do. The plan for today is to take the first 25 minutes. We are going to review a little bit of the stuff we covered at the end of class last time, the electric field stuff. Draw some field lines and do a problem. I'll get as far into problem, I think it's problem number 11, hold the B's, that's the hardest one. It's the hardest one because it's got trigonometry on it. Conceptually it's not that difficult, but mathematically it's a little tricky because there's trig. So we'll get as far as we can in that. I did make, because it's the first homework assignment, and to save me some trouble in responding to people over the weekend, I made a video of myself setting up the problems. I posted it. It's not. I can't talk. It's not available to you right now on Blackboard, but it's on Blackboard. So when I go back to my office, I'll click the reveal the students button, and you'll be able to see it. Please don't go to that first. Try it yourself first, and when you get stuck, go look up and see how I set it up. Now I did it in the middle of the night because like it just occurred to me that that's something I should do. So hopefully it sounds good. I haven't watched it myself. If it's still confusing afterwards, then email me and let me know. I did send it. Did I send you the video of me setting them up?
Yeah.
Was it good?
Yeah.
Okay, good. Did you watch it?
I did watch it.
All right, good. So, all right, so that's that. Let's get started on content. I want to go to the quiz at about halfway through the class, so tell me, can you keep an eye on the clock and tell me when we have 25 minutes left? No, we do not. Don't gaslight me. We talked about Coulomb's law. Coulomb's law was for defining forces. The force on a charged particle equals K, Q over R squared, where Q is the charge of each thing, and R is the distance between them. That distance is squared. It's in the R direction, so it's radial. It's along the line between them. It's either towards or away, depending on whether they're the same charges or opposite charges. Force is measured in newtons. We covered all that stuff. We also said it's useful in some cases to generalize not for a specific charge, but for any charge and what force it's going to feel. There's a homework problem number 5, I believe, where it says place a charge where the force on it would be 0. Do you remember that problem? It's a little bit tricky. Once you kind of figure out how to do it, there's actually 2 methodologies, 2 ways to do it. You can do it in terms of the equation that was just on the board and disappeared, in terms of the forces. And you can set the net force equal to 0, and then calculate it out, and that charge that you don't know divides out. Or you could look at it in terms of electric fields, because remember we defined the electric field as the force per unit charge at a certain spot in space. So if I know that the electric field is 0, then any charge that's at that spot is going to feel a force of 0 at that spot. So we could use our electric field equation from the 2 point charges and figure out where the electric field total would be 0. The equation for the electric field from a point charge I gave you last class, it was E field equals K. I can do a better K. K Q over R squared, where Q is the charge that is creating that field, it's making that field. Not the thing feeling the effects, but the thing that's creating the field, that is making the effect. Does that make sense to you? Because it's the amount of field that is being made. And that's the field due to a point charge. There's a homework problem that talks about 2 pieces of tape. We treat them as point charges. It's really super convenient to treat things like point charges instead of charge distribution. If you have a distribution of charge, sometimes you need to use calculus. We just don't want to do that. It's not this. You want to do calculus? Or just go into that?
No.
She pointed.
I don't know what calculus.
All right, fair enough. Calculus is fun. It can be. All right, I got to fix this. It keeps going to sleep really fast because it's in power cycle mode. Aren't we all? But if I have to be awake, so does my iPad, so give me a second. This equation we derived from the definition of what an electric field was. We said that the electric field is the force per unit charge. And from that very same equation, we can write the equation to find the force on a charge that's in an electric field. This is of the exact same format as F equals ma, or force of gravity. Remember, force of gravity is kind of a corollary to electrostatic forces. They're mathematically very similar. F equals m times g, the force of gravity. The corollary term for m would be this scalar quantity q. This is like the lowercase g vector, the acceleration due to gravity, or also known as a gravitational field strength, if you want to call it that.
So electric field is kind of like the gravity in our sense, like how much
Kind of.
force it feels on itself.
Yeah, so right now I'm feeling a force downward towards the Earth.
Okay.
If I'm jumping out of an airplane, I'll feel a force downward towards the center of the Earth. The moon feels a force towards the center of the Earth. Actually, the sun does too. This is not affected as much because it's got so much mass, but it does feel that force. Anything with mass in the universe is going to feel a gravitational force towards every other thing that has mass, because we exist inside of the field created by it, the gravitational field. So that's a really good way to look at it. They're very similar in concept. So at the very end of class, I was talking about drawing field lines. I had a question on the quiz about field lines, but since I only barely got to it, I nixed that one. I took that one off. I mean, thumbs up, but it's not that far. But it was new. And it was like anything that you don't know how to do yourself, right? So until you know how to do it. When you're drawing field lines, because it's not on the quiz, but it will likely be on some assessment at some point, test or otherwise, where you have to either look at them and understand them or draw them yourself. There's a couple things you want to keep in mind. If I have a positive charge, let's say I just have some ball of conductive material that I put positive charge on. It will produce an electric field that radiates out from it. Rule number one about drawing electric field lines is that they go out from positive charges and into negative charges. If you think of like a really big flat table, if I'm pouring water on the table, that water just spreads out in all directions. That's like a positive charge. It's like where the faucet is dropping water on the table. A drain would be a negative charge, where all the water comes into. All the electric field lines go into the negative charge. So for electric fields, they come out of positive charges and into negative charges, and they never cross. So if I have that positive charge right there, I'm going to draw my field lines straight out from it. They radiate in all directions straight out. I could draw an infinite number of these, but I actually can't draw an infinite number of them because I don't have enough time or patience to do so. They just radiate in all directions. Is there a field line coming out this way? Yes, but I'm not going to draw it. I'm just going to draw some representative samples. If I try to draw all of them, you can't. You can't draw infinity, right? You can't just draw it until forever. I couldn't. There's just not enough time, and my pen isn't sharp enough. So instead, we just pick a set of representative samples. It also allows us, bless you, to show relative field strength, because here's rule number two: where the field lines are closer together, the field is stronger. I think I mentioned that in class last time. If I was to double the amount of charge in that ball of charge, I would have to draw more field lines to represent more electric field, stronger electric field. It also shows where in space it's strongest. Where are the field lines closest together? You can look at the picture. Where are they closest together?
Closest to the charge?
Yeah, the closer you get to the charge. If I make a circle that's this big, and I try to capture as many field lines as I can, if I'm way out here, I can at most get one. But if I'm in here, I can get, wow, I can put 3 in that circle, because they're closer together. The field line density is higher. Where the field line, this is another rule. There's no specific numbers here, just I'm giving you all the rules. Where the field lines are closest together, the field is the strongest. and erase the whole thing. If that was a negative charge, what I said,
Next to that thing.
why did I do that? Kind of cool to do something like that. Oh, come on. If instead it's a negative charge, the field lines are going to go in towards it. The field lines, this is another thing I said in class, and I know I said it because you made me say it like 5 times. And I didn't say it exactly the same every time. The field lines point in the direction that a positive charge would feel a force. So the direction of the field is the direction positive charges would feel the force if you put them in that field. So for a negative charge, the positive charges are going to feel forces towards them, right? So the lines go towards it. So they come in from all different directions. Once again, getting more dense as they get closer. Point again. They don't cross because they're vectors. Electric field is a vector. And anytime you have 2 vectors that overlap, the superposition principle says they just add up as vectors. So you don't have 2 crossing lines, you have 1 line that is the sum of those 2. So they don't ever cross when you're drawing. No crisscrossing lines. You only have, at any given spot, you only have 1 field, 1 amount of field, 1 field vector. Yeah.
So, for that stuff that we measure repeat a bajillion times, so basically everything's always going to be pointing away.
If I drop a positive charge right here,
Right.
where would it go? We get pulled towards. It would feel a force, attractive force towards the negative, right?
Right.
So the line would go that way. If this was positive, it would get pushed away.
So
the
it's
line would
always
go
going out of the positive.
Yep.
Okay.
And into the negatives. That might have been my rule number 1, I don't remember. They're all, I numbered them just in the order they occur to me as long as I cover them all. What if I don't have 1 single charge? What if instead I have a positive charge and a negative charge? What would my field lines look like? Well, in between them, I think you're right. Because if I drop the positive charge right here, it's going to get pushed away from that one and pulled towards that one. So it's going to be a straight line, one to the next. Out of the positive into the negative. What if I drop the charge right here? Which way is it going to feel a force? Well, it's going to feel a strong force that way from this one. But it's also still going to feel some force, smaller but still existent, towards that one. So it's going to be kind of maybe not directly up, maybe at a little bit of an angle. And as I move, this one is going to have less effect, and this one is going to have more effect. So it's going to start to curve as it goes towards that negative charge. So the field line is going to look something like this. Same thing on the bottom, because symmetry. Symmetry is our friend in electrostatics. If I go straight out the top, it's going to feel a force, a strong force up, but that negative charge is still going to have an effect. And as it gets farther away from the positive, the negative has more of an effect, and it's going to curve as well. And come in to the negative, out of the positive into the negative, out of the positive into the negative. Out of the positive, all the way around, into the negative. Out of the positive, all the way around, into the negative. Out of the positive, and then from infinity into the negative. So we get a set of field lines that go out of the positive into the negative. Following our rules, there's no crossing of them. The field line density represents the strength, so where is it strongest? Still near the charges, where they come together. Where is it weakest as you get farther and farther away? One of the exercises we do in our upper division physics class that I'm not going to make you do, but it's just kind of, it's a mental exercise to think about. I see it. If you zoom way, 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 way out, then the fields look like just like a group of charges, not as, you don't see the fine details. So you either see them coming out or coming in. And this would look neutral if you zoom way, way, way. If I had 2 positive charges, the field, when you look close, is really interesting. But when you zoom out, it just looks like a positive charge spreading out.
So just to clarify, the lines are curving like that because there's a negative charge like farther away?
So
Or like, why are they curving?
right here, if I drop the positive charge,
Oh,
it's going to feel a strong force from this one and a weak force from that one.
okay.
So it's going to get pushed farther up. But as it's like, as I let it go and it starts moving, as it's getting farther away from this one, the force from this one is smaller, Therefore, the field is weaker, and it's going to feel more of the effect from this one. And at some point out here, it's going to start feeling this one as much or more.
And that's what
So it
brings
starts
it back.
curving around. A field isn't a tangible, like you can't feel it necessarily. I can't see it. You can see the effects of it. And that's what this is. We're drawing what the effect would be. We're visually representing a very abstract concept. That's what the lines do. It's like a topographic map. It actually becomes very literally like topographic map. That's next class. That's going to be on Monday. Okay. What if it's two positives, and then we're going to move on? What would that look like? Cool, I can clear all just on one slide. I was worried I cleared the whole slide. What if I have two positives, or two negatives, but we'll start with two positives. Let's say they're two equal positives. What would the field be right here, exactly in the middle? What? 0, it would be 0, because the field due to one would equal out the field due to the other, and they're in opposite directions, so it would have a vector of 0. Exactly, it'd be 0 right in the middle. But you said it's kind of going to go out, away. Because if I drop the positive charge, over here, it's going to feel a force from both of them pushing out. Same thing on the other side. So the field lines are going to go out, for sure, from these. If I drop a positive charge right here, it's going to feel a force up from this one and a force away from that one. So it's going to curve away as well. Field lines that are going in, this is our logic Ava from before. If I drop the positive charge here, it's going to feel a strong force that way and a weaker force from this one this way. But as it gets farther away from this one, it's going to feel more of that one. It's going to get curved away again as well. So the field lines are going to look something like this. Yeah.
So would there kind of be like an asymptote or something in the middle, like that it
Yeah.
would like get really close to but never like cross
Yep.
over them?
Good use of the terminology. All right. Moving along, because I'm going to shift gears a little bit. I want to get this sample problem at least set up for you. And I want to make sure we have time to get to the quiz. I don't know why they use bees. Although bees do use electric fields to communicate, they charge themselves as they rub against the flowers, and it creates electric fields that mark the flower as having been visited already, which I think is super cool. There's a link to a description of that in Flagwood somewhere. So that is super neat, but the fact that they use bees here is totally irrelevant. They could say it's anything that has charge on it, so don't get distracted by the cute little bee picture. If you have a phobia of bees, don't be scared. They're pretend, they can't hurt anything. So it says we have 3 charges, B1, B2, and B3. We are given the amount of charge, and we're asked to find the, let's say field or force, the field, the electric field, at the spot located at B number 3. That's already a tricky thing. It's already trying to trick you, which I don't particularly like, but it is, because at that spot, we don't care about the charge that's located there, we just care about what the effect is on that charge. So there's 2 different ways you can approach this, and they're both equally valid. In the end, the math is exactly the same, but conceptually, there's 2 different ways you can approach this. You can calculate the force vector on that B for that charge. That's great, you can do that, because you know how to do that. That's with Coulomb's law, F equals K QQ over R squared. You do it twice, you add the vectors, you get your result. I'm going to show you how to set it up, but that's just one way of thinking about it. Once you have the force, once you know the force, you're going to look at the shadow of Dr. Treese's writing on the board. Once you know the force on that charge, and you know the amount of charge, you can plug them into this equation and get the electric field. And the direction for that electric field is going to be the same direction as the force.
Is the Q in that equation like the charge at B3? Or is that?
Yeah, remember that for this equation, it's the Q that's making the field, right? For this equation, it's the Q that's feeling the effects, it's feeling the force on the charge. Make sense? So that's method number one. Perfectly valid, works great. Method number two is you use the E field vector equation for point charges. We take out B number 3. We don't even look at its charge because we're dividing that out of the problem anyway. And we say, what is the electric field strength at B number 3? I calculate the electric field strength for B number 1 at that spot. I calculate the electric field strength for B number 2 at that spot. And then I add the two vectors together to get my answer. So both of those ways, in the end, are the same. You're taking in a certain amount of force dividing out the charge. You can either divide out the charge at the beginning, looking at the E field with the equation, or you can calculate the forces and divide out the charge at the end. You get the same thing. Yeah?
Wait, so if we're focusing on B2,
B3.
or, yeah.
Yeah.
So
It
which,
says the field at B3.
so which one is the, that you insert for the Q again? For the E equals force over?
I'm not sure what you're asking, but I'm going to answer what I think you're asking.
Yeah.
You tell me if I get it right.
Yeah.
For this equation, you know what, I'll just put it back up on the big screen. I don't like looking at his erased stuff. Because I have these written already. When you're looking at a force, you have to look at both charges.
Yeah, so that
because
would
they're
be
both
like,
affecting each other.
yeah, like B1 and B3.
Sure.
Okay.
Yep. So we're looking at the force on B3 from B1, so we put both charges in and we calculate it. If I'm finding the electric field at point 3, that electric field comes from two different charges. One part of it comes from B number 1, another part comes from B number 2. To find the field at that spot from B number 1, I put in Q1. To find the field due to B number 2, I put charge number 2 here. If I want to find the force on a charge that's in a field, I'm going to use the charge that is in the field in this equation. This is the one that's making the field, to find how much field it's making. This is the one that's feeling the force, to find out how much force it's feeling.
Okay.
I can't say it better than that.
Yeah.
So if you need to
it's
hear
just
it,
gonna, it's
yeah.
gonna.
If you need to hear it better than that, I can say it again, but I'll probably say it the same way. You could look it up, read it in your book, find a YouTube video, talk to Dr. Treese, he might have a special way of saying it. But, or you can ask me again, I'll try again.
Are you able to set this up with numbers?
We have a problem with B's, want to do that?
Well, I didn't know if you were just gonna write the equations or put numbers in.
Well, we'll see. I've got, how long, 5 minutes?
Two.
I have 2 minutes, so probably not, just write the equations.
Okay.
Yeah.
If I'm calculating the E field vector, I'm going to do it the second way that I said it. In the end, the process is the same for both. Like I said, you're just dividing the charge at the beginning, dividing the charge at the end. It comes out the same. If I am setting it up the second way I said it, I'm going to use my E field equation. Remember that electric fields go away from positive charges and they go towards negative charges. In my problem, B1 is a positive charge. So B1 is going to produce a field at B3 that is directly away from it. If I drew a straight line from B1 to B3, the field is going to go directly away, and it's going to have a magnitude equal, so I'm going to call it E field 1, because it's from B number 1. It's going to equal K Q1 over R1 squared, where R1 is the distance between those two B's. It doesn't give it, but it gives the two legs of the triangle. You can use the Pythagorean theorem to find the third leg. B number 2 is a negative. That means that the field due to B number 2 is going to be towards B number 2. That one's convenient. Actually, that's the one I started with when I did the problem myself, because it's in a straight line. It's only going in the x direction, so I don't need to do any trigonometry for that one. I will need to do trigonometry for the B number 1 field. For B number 2, to find E field number 2, it's going to equal K Q2 over R2 squared. And R2 is just 10 centimeters, so that's how far apart that is.
For Q2, you would just use the four, if you don't use anything with the,
Use the what?
E3.
No, because I'm finding the electric field due to V2.
Oh,
And this is the charge that's making the field, this is the charge that's making the field. To get my final answer, I gotta find the sum of those two vectors, the resultant of these two vectors, E1 and E2. E2 is going to go in the negative x direction, I know that. It's a negative x quantity. So it doesn't have a y component, it's no up and down, it's just to the left. E1, it's got two parts. It's got a part going this way, and a part going that way. That's where you gotta do a little bit of trigonometry, because you're gonna need to find the angle. You can find this angle easily enough with the inverse tangent of 10 over 5. Use your geometry knowledge to know if you know this angle, you'll know that angle, and then we can figure out what this angle is. From that, you can use your sine and your cosine to find the legs. Those are in the positive and the negative y direction, positive x and negative y direction. You put the components together, and that's how you get your answer. It looks simple that way, doesn't it? It's not. It takes some time. If you need help with it, you know where my office is. I do have a meeting today at 1, so I'm not going to be in my office hours until about 1:45. I apologize for that, but I'll stay a little bit later if you need me.